So, hello everyone, I'm Veselin Dobrev and I'll present recent developments in the MFEM library on behalf of the MFEM team. Let's see, I need to click, okay. So my first slide is kind of a summary slide that we have been using for a long time. I don't know, how do I get this like laser pointer? Just sorry. Pointer options, laser pointer. Okay, first time using it. Okay, so yeah, so this is basically a list of the capabilities of MFEM, and I know that Tanya covered a lot of these, so I don't think I need to go into details. Basically discretizations, various discretizations, support for different, IGA, DPG, standard Galerkin, a lot of linear algebra, a lot of it goes through hyper, time stepping, nonlinear forms and problems, examples and mini-apps, and a lot of integrations with a growing number of external libraries. Okay, and so this is a slide that kind of illustrates that those connections. So MFEM, with this is the direct integrations we have, and well, some of them are actually we have now direct integrations with these two, for example, with this one as well. As being part of the seed co-design center in the ECP, and a lot of the application, I think Tanya also showed them. So a large ecosystem of software, and we are trying to be connected to a lot of software to provide, the power of all these software developed by so many people in the world, really. Okay, so some of the connections from kind of written down, like the XSDK, so the Extreme Scale Scientific Software Development Kit, or known as XSDK. We are part of that project, and we're part of the FASTMath Institute, and engaged in SciDAC collaborations with RF SciDAC, TDS SciDAC. So this is kind of a background. Okay, so going now to what is new in the new release, mostly. So some of these is just really concentrated extracts from the changelog, and I've tried to highlight some of these features that I'm listing here. So submesh extraction and field transfer functionality. So this is something that was developed by Julian Andre, and it is kind of should serve as a basis of implementing basically multi-domain problems where you have different physics in different subdomains, and you want to connect them through fields or through interfaces, and this is providing kind of the basis for discretizing this type of problems. So second bullet, functionality. So this is something simple, but could be very useful to people, functionality. So you have a parallel mesh, but then you want to just combine it into a single rank for, maybe for use somewhere else, or for whatever reason. It's kind of a small, nice feature that was added recently. Another meshing related feature is we've extended the 3D TMOP matrix. So TMOP stands for target matrix optimization paradigm. So this is a mesh optimization paradigm for via node movement, and we've been doing a lot of work in the area of optimizing high-order curvilinear meshes. And in this new release, we have new metrics, specialized matrix for untangling, and for controlling worst case quality. So these are new options in that area of optimizing meshes, and specifically focused on high order meshes. Another feature related to meshing, we have now support for mixed meshes and pyramids in the GS library integration, which is library for interpolation between arbitrary meshes. If you're not familiar with GSLib, that's one of the main things you can do with GSLib. Basically, so it's at 5 points here, basically given a set of points in physical space, it can find their location in local, in each local, which element it is and what's the local coordinate in that element. So that's very powerful tool for various algorithms. Another new feature that was added in this release is linear form assembly on GPUs, which is something we've been lagging behind on, and now it is available and uses, improved algorithms, kind of a matrix-free type ideas in the implementation, which is suitable for GPUs, but also for CPUs, and can provide a nice performance boost in also in CPU scenarios, not just GPU. So another GPU-related improvement, which actually is kind of connected to the previous one, support for coefficient evaluation on GPUs. So this is something that we had some support in specific cases. Now we have a more general approach where, even user-defined coefficient classes can implement their evaluation on GPU if they wish to do so. So we have a big point is improved low-order refined solvers, and this covers the whole DRAM complex, and we have some very nice implementation of a FastDG mass inverse algorithm, and I believe this bullet will be covered extensively by Will in his talk later. Okay, so as a first highlight, I want to mention a few things regarding the kind of more details on the submesh extraction, what it is and how it works and what you can do with it. So basically, this implements two new classes, submesh and parsubmesh, and they inherit from mesh and parmesh. And that means that any of the other classes in MFEM that take mesh or parmesh input, they can also use submesh or parsubmesh, respectively. So this is just a way by subclassing to introduce this concept of submeshes. And an important extension here in the submesh is that it preserves the knowledge of how it's connected to its parent. So, and that will allow us to do field transfers, which I'll mention in a minute. So what you can do is basically submeshes can be subsets of volume elements or boundary elements. So you can do, you can extract subdomains, so like a sub part of the domain. You split your domain in some number of parts if you want to do maybe fluid structure interaction. Or you can do boundaries, and this could be useful for maybe doing interface processing. So you restrict your data to an interface and you transfer it then to the other side, or maybe you can even define certain forms on boundaries if that's what your discretization needs. And currently, the submeshes are defined either through volume or boundary attributes. And this is not a big limitation, I think. Can be easily extended to do arbitrary subsets, I believe. And then the important feature is field transfer between grid functions between these different meshes, and we do support basically all transfers of interest. So we can go from a parent mesh to the child submesh to the child mesh, which is another term for submesh. You can go in the other direction from the child to the parent, and kind of based on these two, you can then go between any two meshes that share a common ancestor. Basically, follow a sequence of transfers in a kind of a matrix-free fashion, generally.
Excuse me, Veselin. I
Yes.
have a question. This is Walt Neeson from Lawrence Livermore. Are all the field data grid functions? Is this a general capability then?
So fields that are defined through finite elements, they're represented by grid functions in MFEM. So any finite element type data, yes, you can transfer. Now we have another type of data, which is quadrature point data. And for that one, actually, I'm not sure if this is actually included in the current release, or this was something that we could do later if needed, when needed. So I'm not 100% it's there, but we can also transfer, I think, or add easily the capability to transfer quadrature point data as well.
Great, thank you very much.
Okay. And then, as I mentioned earlier, goal is to serve as a basis for multi-domain problems, different physics in different domains and things like that. Okay, so next highlight I want to mention, highlight the feature that we added recently, the linear form assembly on GPUs. So this is very much transparent to the user. If you want to enable it, you just need to call used fast assembly through this method in your code, and then the linear form, when you assemble it, it will basically branch to use the new algorithms. And I've listed the type of integrators we currently support. So this is something that's will be ongoing work, extending to other linear form integrators, but these are the basic ones that are currently supported. Of course, they support each form needs a slightly different kernel or set of kernels that need to be implemented. So there is a way to, for linear form to check if the integrator is GPU or fast assembly enabled. And if it's not, it's going to use the standard assembly. If it is enabled, it can use fast assembly. And basically, the main ingredient in the linear forms, or one of the main ingredients, is really any coefficients that are included, that are provided to the linear form integrated construction. Coefficients, their fast evaluation is essential for performance. So that's why we also looked at the next topic, highlight here, coefficient evaluation on GPUs. So, so right now, so what we did really is something simple, I think, and easy to use. So it's an extension. So if you have a coefficient, and we have a number of coefficient classes in MFEM, you need to define the project function, which basically will project the coefficient globally everywhere. And this is unlike the current interface or the legacy interface, which uses evaluation, like a virtual function, to evaluate values at one quadrature point. So by evaluating it, this big set, this could lead to a lot of performance improvement, big performance improvement. And as I said, the idea is user-derived classes can basically override the project methods to provide their own GPU implementation or just even CPU implementation that's faster than calling the eval method for every quadrature point. So internally, there is another class that serves kind of as a conduit to connect the different coefficients. Or we have coefficient, we have vector coefficient, we have matrix coefficient, and we have abilities to project these these coefficients on a volume or on a surface. So all these kind of cases are handled in this kind of auxiliary, somewhat internal class coefficient vector. And we also use this class as a storage, but also to give us the ability to provide fast evaluations for scalar coefficients, for example. There is no need to evaluate them everywhere. It's a very natural, simple optimization. And then we also have code paths for grid function coefficients and quadrature function coefficients. So those can be also evaluated on GPU if configured. And the base class, the generic implementation, just uses the legacy eval methods. So for any classes in MFEM or user classes that do not implement or overload project, they'll basically revert to the legacy eval method. So things will work, maybe not efficiently as one will want, but they will work. Okay, so this is a summary of the coefficient improvement. So let's continue with some other developments. So there is a new patch recovery-based a posterior area estimator. So this is actually closer to the classic Zinkevich-Zoo error estimator. The error estimator we have in Zinkevich called Zinkevich-Zoo is actually a variant of Zinkevich-Zoo. It's not kind of the original patch-based algorithm. So this is more of a classical, maybe with a twist still, but just another error estimator that actually can be quite good in practice. So there was a contribution that we also merged recently, so more flexibility with constraint solver classes. So if you're using those, you can check out the new extensions. So we have a few new mini apps. So one of them, I think Tanya also mentioned it. It's the Hooke mini app, nonlinear elasticity. It's using AD, and the AD could be their simple built-in implementation or via the enzyme library. Another mini app is a body-fitted volumetric and shape integration using the algorithm library that's available as part of the shifted mini apps. So this is a mini app inside the shifted subdirectory. And a new example 33 and 33P. This is an example of solving spectral fractional PDEs, something a new type of PDE that you can check out if you're interested in fractional PDEs. And I already mentioned the enzyme AD2 that's used in Hooke is we have support for that, illustrated in Hooke, and then support for the par moonlit library, which is another library for data transfer between meshes. Okay, and so as a highlight, the Hooke mini app. So this is a static nonlinear elasticity solver using what I call a kind of matrix free type algorithms. So matrix free is in quotes because it's nonlinear, so these are not really matrices. So it should be, there is no matrix, but the type of algorithms have use ideas from this matrix free type algorithms. So this is a customizable. It has customizable elasticity models with linear elasticity and new Hookean elasticity provided as examples. And it can use AD to evaluate the gradients of the model. So in the best case, you can just specify your, energy density function, or if I remember correctly the term, and then from that, the model can differentiate it automatically. So you don't need to worry about that part. And that could be achieved by a simple built-in AD or using the enzyme tool, as I already mentioned. Okay, so that's a short summary. And just to finish the list of new things that might be of interest. So we have now support for GPU support for mixed meshes. So if you build MFEM with libseed and you use the seed backend, this can be, you can do computations on mixed meshes, at least with some integrators. I don't think we support all the integrators, but at least some of the integrators do support this new feature. And we've started a benchmark kind of suite. So this might be the first installment, and a benchmarking for the different assembly levels that are provided in the new matrix free type partial assembly or element assembly or full assembly type algorithms. And this is inspired by the seed bake-off problems. And lastly, but maybe not least, if you're a Windows user, this is something that could be interesting to you. We do test Windows now constantly on GitHub for any problems there. So Windows is one of the platforms that we are testing on. I know that we have a maybe not very small percentage of users that are interested in using it in their Windows. Okay, and with that, I'll stop here and thank you for your attention. Any questions, comments?
Hi, Veselin. I have another question that's sort of more general. If I've got my fancy new GPU, my integrator picked and my mesh and all that, is there a nice diagnostic so I can tell whether I'm getting GPU accelerated? Or is it just thing you have to sort of look up in the documentation under each, each component, or, how does that work in general?
I guess there are different. So for linear form, as I mentioned, the linear form has basically a method that says I can do GPU or not. So that's kind of you can check for the linear forms that you use if that's yes or no.
You can check at runtime from just by calling on that component.
Yeah, you can check it on runtime, or you can check it, beforehand. Yeah, it's it's for each specific class. It's just a constant that does not change. Now, with respect to bilinear forms, in that case, I think what will happen is if you enable, let's say, partial assembly for GPU, it will call certain method in the bilinear form integrator. And if that's not overloaded in this class, it basically will call the implementation in the base class, which will give basically a runtime error that, yeah, this method is not implemented for this class. So it's not, it's straightforward, I guess, to to figure out which methods, which linear forms are available for GPU, which are not. We may have a list online, but I'm not 100% sure if that's true. Tanya, do you remember if we have a list of what's GPU enabled and what is not?
Yeah, we do. It's on the performance and partial assembly, I think, on the website. Sorry, I'm looking at it. Walt, is your question about GPU support in the different bilinear and linear forms, or is it about other components of that? For example, I'll just guess here next.
Well, yeah, I was more asking generally, not specifically for, the bilinear form per se, but I was just trying to get a sense, if, let's say I have a miniapp, right?
Yeah.
And I want to know, have I chosen, an integrator that's going to be GPU enabled on the platform I'm on, things like that, just sort of, how do I choose, if I want to try to make best use of my GPU? And so I think you've given a very helpful answer, Veselin, and yeah, if there's a list somewhere, that's great.
Yeah, I was trying. Tanya, do you have the link? Maybe we can link the in chat.
I'll try to find it and follow up.
Great,
Yeah,
thanks.
I'll look at that as well. Maybe it's just the list on the website that we have with the integrators.
I thought we had
There was a checkbox if it's GPU enabled or not, but I'm not 100% sure. So I'll try to figure out that and post a link if we have something like that could be useful for everyone, I guess.
Awesome, thank you.